Page 17, we start some optimization problems. And optimization problems are very real life because take the example of like the IB program. The more you study, the better grades you get. So why don't you just study like 50 million hours a week, okay? Why don't you just study, 30 hours a week? Well, if you start studying 30 hours a week, then you are going to start sleeping less, and then you're going to get sick, or you're going to not wake up in the morning, or you're going to sleep in class, and all these factors are going to cause you not to get good grades. So do you see how just putting blindly more time into the IB is not going to get you better grades, right? It's like the more you increase the amount of time you study, in the end, there's other factors which are going to make your grade worse. That's an optimization problem, right? You can't just blindly increase one of your inputs to make the output go up, okay? So that's exactly the philosophy that we're going to be using here. And let's take a look at problem 9. An open box can hold 80 cubic centimeters. It is made from a square piece of tin plate with 3 centimeter squares cut out from each of the 4 corners. Find the dimension of the original piece of tin plate. What the heck do they mean by an open box? Well, the thing is, if you take this tin plate and then you fold the edges up so that you would make like an origami box out of the metal, you would end up with kind of a box with no lid, right? Which is the open box, okay? So this open box happens to have a volume of 80 cubic centimeters, okay? The volume is 80. It's made from a square with 3 centimeters. It's made from a piece of tin plate with 3 centimeter squares cut out. So this is a 3 centimeter square that they cut off, right? Find the dimensions of the original piece of tin plate. Okay. They're starting off easy here. I don't think this is even an optimization problem, really. Okay? Not yet, anyway. Okay. But we'll get there. So, what is the volume equation? The volume equation is length times width times height, right? Okay. So basically we have 80 equals length times width times height. Okay. Do we know length times width times height? Well, it's a square piece of tin plate, so what if we call the original dimension of the tin plate x? If we call the original dimension of the tin plate x, then we know both sides are x because it's square, right? So I would say that the length and the width of the original tin plate is called x, right? But the length and the width that we're talking about here is this and this, okay? So L is actually x minus 3, right? And width is also x minus 3 minus 3. So actually our length is equal to x minus 6, and our width is equal to x minus 6. What about our height? Well, once you fold it up, do you see how this dimension here is actually the 3 centimeters we cut out? So the height is 3. So I'm going to put my numbers in here. So I'm going to put length is x minus 6, width is x minus 6, and height is 3. So can we solve this equation? Well, it's going to turn into a quadratic because, remember, this chapter is the quadratics chapter. So now I'm going to multiply these two together. So I get x squared minus 12x plus 36. Now I can distribute the 3. I'm going to distribute the 3 to all the other terms. So it's going to be 3x squared minus 36x plus 36 times 3, which is 108. And that's equal to 80. Now I'm going to combine like terms. I'm going to subtract 80 from both sides so that I can have 0 on one side, which is exactly how we solve quadratics. So then I get 28 left over here. Okay? I would factor out the 3 to see if this is factorable, but guess what? The 28 is not factorable by 3 unless we want a decimal, which we don't want. So this is a job for Poly SMLT. Okay. reset. Okay. On. Oh, PolySMLT. Apps. PolySMLT. Enter. Okay. Polyroot Finder. Order 2. Next. Okay. And then we just put in our coefficients. 3, -36, and 28. Solve. So the two possibilities are 11.1 and 0.836. Okay, 0.836. Okay, 0.836 is less than a centimeter wide. If x was 0.836 and you subtracted off 3 centimeters from it, you would have a negative dimension, so forget 0.836. What you want is 11.2, right? So the solution we want is 11.2 centimeters. So the original piece of template was 11.2 by 11.2 centimeters. All right, let's go down to 11. That wasn't too bad. It wasn't even an optimization problem. They were just getting almost warmed up. Oh, the golden ratio. If I have one piece of advice for you on your IA, don't do your IA about golden ratio unless you want to be the same as 30% of all IB Math SL students in the world. Okay? All right, so the rectangle ABCD is divided into a square and a smaller rectangle by xy, which is this, which is parallel to its shorter side. The smaller rectangle BCXY is similar, which means it has the same proportional dimensions, to the original rectangle. So the red rectangle is the same shape as the blue rectangle. It's just proportionally smaller. Okay, so they give us some advice here. They said, say that AB is x units. So this is going to be x, and AD is 1 unit. Okay? So if we say that this blue rectangle is the same proportion as this red rectangle, then let's see, what would we, oh look, this dimension of the red rectangle is also 1, right? Because it's the same length as the blue one, right? And there is an unknown length here. We'll call it A. But do you see how A is related to both 1 and x? Because, like, look, this is a square, right? Since that's a square, we know that its dimensions are 1 and 1. So if I wanted to figure out what A is actually x minus 1, right? Because x minus 1, right? Okay, so now I can write a proportion between the blue rectangle sides and the red rectangle sides. For example, the short side of the blue rectangle divided by the long side of the blue rectangle should be equal to the short side of the red rectangle divided by the long side of the red rectangle. Okay, so if that's true, we should be able to figure out the length of side x, and it'll turn out to be like the golden ratio length or whatever. Okay, so now I'm going to make this into a quadratic, of course, because again, we are in the quadratics chapter. All right, so I rewrote it. I took off that 1 in the bottom because it doesn't mean anything. Now I'm going to multiply both sides by x, or I'm going to cross multiply, whatever you want to call it, just so that I get everything in the numerator. Because that's the first step. Whenever you have an x in the denominator, you need to get it to the numerator. So I'm going to multiply both sides by x, and that's what I get. Now, since it's a quadratic, I do need to solve it by putting 0 on one side. So I'm going to subtract 1 from both sides, and that gives me this. Now, is this solvable with factoring? Of course not. Then the golden ratio would be an integer, and it's not. So, okay. Oh, well, we have to show that the golden ratio is going to give us this value, and the only way we're going to get that value is if we do quadratic formula by hand. So forget PolySMLT. Okay. So now we have A equals 1, B equals -1. and c equals -1. So let's see. X equals minus -1 plus or minus b squared minus 4 times a times c. Right? Divided by 2. Do you see what I did? Every time I had a 1, I just ignored it because times 1 does nothing. Every time I had a negative, I changed the sign. So -1 is 1, plus or minus the square root of 5 divided by 2. Oh, it worked. Okay, we got that. All right? All I did was substitute these values into the quadratic formula. So I'm done. That was page 17.